the idea here is you got something. Our examples are going to be lists of numbers, and for whatever reason you want to sort them. Sort of a practical, if you will, example, I have to admit, when I started helping people out with courses was dealing with if you're grading for somebody and you decide that you need to sort the papers. So like if they're actually hard copy, that would be another thing that you're sorting, okay? And I remember when going through that, I was like, I'm using such and such sort algorithm at the time. But in terms of sorting, it doesn't matter what it is that you're actually trying to sort. The key thing is you have X number of objects, or really N number of objects in the notation we're doing, N because it's an integer or counting number. And then you want to put them in a certain order. That order is designated ahead of time. Okay. So in terms of the stuff that we're looking at, we are looking at where we compare two items of our list of items at a time in terms of actually building a binary search tree that corresponds to looking at two items at a time, so the behind-the-scenes stuff, whether you actually build this tree or not. That sort of tree has at least n factorial leaves, and what we found was if you're looking at the height of this tree, it is at least as tall as, and this is a formula that we had previously, the ceiling of log base 2 of n factorial, which is, roughly speaking, order n log n. Okay. All of this makes the assumption that the tree that you're dealing with has n vertices. Now, that got us into the fact of looking at our theorem, which said that the number of binary comparisons needed to sort n items is at least order n log n, and notice all of that does actually come from this behind-the-scenes stuff. So regardless of whether you built the tree or not, if you're dealing with these sorting algorithms, you've got the tree behind the scenes. Now, we started looking last time at BubbleSort, and we had the online, I don't even know how old that web page is that we looked at last time, and had sort of the animated-esque version of BubbleSort. But I wanted to go back over it today to make sure we're all comfortable. So you're given some sequence, some list, whatever it is. For us, we're just going to be dealing with a random list of numbers because it's easy to say put the numbers in ascending order. Okay. When you walk through your sequence, what happens if the orders are not in ascending order? In other words, if you've got two adjacent items in your sequence, in your list, and the bigger one comes first, you're going to swap the two. Okay. Please note in terms of this inequality, if you have items that aren't actual numbers where you can do that sort of comparison, this here you'd change out to whatever the comparison is that you actually need, and this tells you that if they're out of order, swap them. Okay. And then you repeat this step until you've been able to go or pass through the entire sequence at least once with no swaps whatsoever. Okay. In terms of what this means, the maximum of n minus 1 passes that you have to go through your sequence, and obviously the algorithm can terminate early. Okay, so our goal here is we want these numbers to be in ascending order. Now, we looked at this example previously, so we're not going to go to that one. So instead, what happens if you had this thing and you were asked to use BubbleSort on this sequence, okay, and you couldn't plug it into an animated version and let the computer do it for you. So in this case, let's look at the specific details, and then the reason for doing this out is I want to look at a property of BubbleSort at the end. Okay. So first pass, what would you do? Well, first pass is you would look at all the various comparisons. So I'm going to go ahead and label these guys. First pass. And I'm going to regret writing all of these out, but we're going to do it, at least for a little bit, because I need to illustrate something. And it's easiest to see this if we actually illustrate it out. So first thing that you do is, and I'm going to go ahead and put this down here, even though it makes our screen a little bit smaller, just because I'm going to color code some things for us. Okay. First thing you do is compare the first two entities. So in this case, 5 is bigger than 1, so we'll swap. So we'll have 1, 5, and everything else stays the same. Then you move the two terms that you're looking for. Instead of being the first two terms, you're now going to look at the next two terms. So in this case, we'll compare our 5 and our 7, and we notice that no swaps are needed here because 5 is smaller than 7. So then we move on to our next pair in the list. So our next pair in the list is 7, 8. So if we look at 7 and 8, we see that 7 is smaller than 8, so there's no swaps whatsoever in the list at that point in time either. Then you move to the next pair of entities in your list, and your next pair of entities in your list is 8 and 2. We see that 8 is bigger than 2, so we'll swap those two guys. Everything else in the list stays identically the same. Then we move to our next pair of numbers in our list, or entities, terms in our list, because they don't actually have to be numbers. You can do this for all sorts of things. And we're looking there at the 8 and the 4. We see that 8 is bigger than 4. So we're going to swap our 8 and our 4. Actually, notice here what happens when you're dealing with this 8. 8 is the biggest number in the sequence. So as soon as we pick up the 8, this guy is going to be moved all the way to the end. And here, if we look at our last pair of numbers in the list, what happens? 8 is bigger than 0. So 8 will get moved into that very last position, which is where he's going to stay for the rest of the time. So notice here as we did a sweep, so this would be one complete pass through the entire sequence. What happened? We compared each one of our pair or consecutive pair of terms of our sequence, and we move things down. Notice at the end of the pass, and this is why we said there was a maximum of n-1 passes. You're not going to do this just once, because here, notice the numbers are still not in perfect order. Basically, what happens with each pass is what? The largest number in the sequence that isn't currently in the place where it should be gets picked up and moved to its correct location. So here, what happened, there was some reordering at the beginning, but the main thing that happened was this 8 got moved to the very end. It's totally hand-waving through the process, sort of layman's terms there. So if you then go and look at your second pass, notice what happens with our second pass. We're going to start with that last term, that last sequence of terms that we had before. Or 1, 5, 7, 2, 4, 0, and 8. And then we'll repeat the exact same process we just did. So we compare our 1 and our 5, which is exactly the same. So no swaps needed whatsoever. We then compare our next terms, our 5 and our 7. 5 is smaller than 7, so no swaps needed there whatsoever. And then we get down to our next two terms to compare, which would be 7 and 2. And here 7 is bigger than 2, so yes, we're going to need to actually go ahead and swap the 7 and the 2. So then we look at our next comparison. And our next comparison would be 7 and 4. Here, notice 7 is the second largest number in this sequence, so that means we're actually going to have swaps for the rest of the time until we've actually put our 7 into the position or its final position, if you will. So our 4 and our 7 got swapped. We'll then go ahead and compare the next set of numbers, and the next consecutive terms here is the 7 and the 0. 7 is definitely bigger than 0, so we'll go ahead and swap our 7 and our 0. And notice here, do you have to compare those last terms? I went ahead and underlined it twice to indicate we may or may not actually compare them. So what do you guys think? On the second pass, would we need to compare those last two terms? Correct. So it turns out if, and this is taking the stuff that we talked about before, if at the end of pass 1, your largest number will be at the end. At the end of pass 2, your second to largest number will be in the second to last position. You could, of course, compare those last two terms, but there's never going to be a swap, so you never have to compare those last two terms. So if you're writing this as an algorithm, you it's personal preference whether you actually write that as a comparison that you're going to do or not, but it's not a needed comparison is the distinction there. Okay. Which means we are ready to actually jump to our third pass without doing a comparison here. So I'm not actually going to compare those two. Let's get back to black. So in the third pass, we'll start with that last sequence. So we've got 1, 5, 2, 4, 0, 7, 8. We'll compare the first two terms, and we see that the first two terms look perfectly fine. So 1 is smaller than 5, so no swaps needed there. Wow, that comma was pretty terrible. Let's fix that. 0, 7, 8. So then we look at our next pair of numbers, our 5 and our 2, and we notice that 5 is larger than 2. So we're going to go ahead and swap the 5 and the 2 to get 1, 2, 5, 4, 0, 7, 8. We'll then look at our next pair of numbers. So this is position 3 and position 4. We compare the two numbers, and we notice that 5 is bigger than 4. Or if we look at, so we'll swap them, or if we look at the sequence in large, we notice 5 is actually the third largest number, so that's somebody we should be picking up and moving along down the sequence. So our next pair of numbers should be 4th and 5th position. We notice that 5 is larger than 0, so we'll go ahead and swap the 0 and the 5. And notice once we swap the 0 and the 5, what do we have? We now have our 3 largest terms in the 3 last positions, so we won't do another swap, or we won't do another comparison is really the thing that we want to say there. So notice that each one of these times, 1 fewer comparisons. Now, next pass, 4th pass through. We'll start with the sequence we got before, so 1, 2, 4, 0, 5, 7, 8. We'll do a comparison. When we do a comparison, we look at the first two terms, and we see that there is no change in the first two terms, so we still have the exact same sequence going on. We then look at the next pair of consecutive terms, the 4 and the 2. We see 2 is smaller than 4, so again, no change whatsoever. But when we look at the next two terms, we have what? We have 4 and 0, and we spot that 4 is larger than 0, so we'll totally swap the 4 and the 0. Now, if you sort of look ahead here, what do you notice about what's been going on for the last little bit? Basically speaking, these terms are in order except for one term, that 0, which really needs to be at the front. So notice here at each time what's happening, at each one of these passes, we're actually pushing that 0 one further towards the beginning of the sequence. And at this next stage, we've put the number 4 into its final position. So these are the 4 largest terms in the 4 last positions. We don't need to do another pass. We don't need to do another sweep through this sequence, or another comparison, I should say, as we're in the 4th pass. 5th pass. 5th pass takes the sequence that we just found and looks at some comparisons. So if we look at the first two terms, 1 and 2 are in correct order. 1 is smaller than 2, so no change there whatsoever. Then the next two consecutive terms are 2 and 0. Well, that's going to flip or swap because 2 is bigger than 0. And at this point in time, 2 now is in its final destination. So we've got, how many terms were actually in this sequence to start with? 7. So we've got 5 out of our 7 terms in their finalized positions. We don't even need to do any more comparisons to get that we are in that finalized position, or permanent position right here, if you will. Now, first two guys, in the 6th pass. Oh, good, I do have extra room. I was worried I didn't have enough room here. So we have 1, 0, 2, 4, 5, 7, 8. That's the sequence we ended with before. we'll look at our first two terms, and we see that, yes, 1 is bigger than 0, so we will swap these guys. Big sigh, finally done. All right, so with this swap, we then get that all of our positions are actually in the correct order right here. Now, in terms of the analysis that I wanted to do of why we wrote all of this stuff out is to talk about how many passes we actually did and the number of total comparisons going on inside of BubbleSort. So let's do a little bit of comments here. In terms of our comments here, we had a total of n equals 7. That is what? That's the number of terms in our sequence. The sixth pass, is the n minus first pass. So that was going to be our last pass through the sequence that we were supposed to get everything in order. Notice we could have done a seventh pass. That would have been totally fine, but there would have been no changes whatsoever. Everybody's already in order. Okay. Now, the other thing that I want to look at here for us is, and let me make it a different color just so it's obvious that we're starting a slight analysis. We want to look at the total number of comparisons. I don't think I already titled that. Oh, I guess I did. I thought I was going to write more. All right, so the total number of comparisons here, and we'll get rid of that bit in a second, goes as follows. So in the first, actually, let me go back to black. In the first pass, how many total comparisons did we do? So scroll back up here. That's what we did. We had a comparison for the first two terms. We had a comparison for the second two terms. Next pair of terms, next pair of terms, next pair of terms, next pair of terms. So that's 1, 2, 3, 4, 5, 6. There's a grand total of 7 terms. We did 6 comparisons. That's 1 fewer. Why would that be 1 fewer? Because we're dealing with pairs. So if you actually look at, and I'm going to go ahead and let's put purple here. You look at the first pair of each of these terms. Notice what happens. You're never going to have the first pair of the pair of consecutive terms be the last number. So it's always going to be n minus 1 comparisons on that first pass. So I'm going to go ahead and put this in terms of n. So this is n minus 1 comparisons. Now, for the second pass, you could still do n minus 1 comparisons, and that's totally fine if you want to do it that way. But what did we say? We said you actually didn't need the very last comparison because the last number was supposed to already be set. So that means if we look at the number of comparisons, 1, 2, 3, 4, 5, and you won't need to actually get to this last one right here because if the very last number is set, there's no way you're going to swap the last pair. Okay? So this is 1 fewer comparisons from before. So this would be n minus 2 comparisons. Any guesses how many comparisons you get in the third pass? Yep, perfect. So each pass, 1 fewer number of comparisons. Now, could you, for each one of these passes, always do n minus 1? Technically, yes, but let's not. Okay. Now, you keep doing this until you get to your very last pass. And notice what we talked about right here. The very last pass was going to be the n minus first pass. So if we're looking at the n minus first pass through the sequence, it would be to use the same analogy. We would have n minus 1 comparisons. How many comparisons is that really? Yep, So that's really just one comparison. Now let's check to see if that actually made sense in terms of what we did. According to this, the very last pass through our sequence, we should have had exactly one needed comparison. So our last pass, yep, we had one needed comparison that we did. Okay. So to get the total of number of comparisons, we're just going to add all of that up. So this is now total. So this would be n minus 1 plus n minus 2 plus n minus 3 dot 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 plus 1. And it turns out that if you actually add that all up, that is exactly n times n minus 1 all over, move, 2. So we're actually doing the analysis of BubbleSort right now. Okay. I just used the formula for adding up n numbers and then reduced it to n minus 1. Okay. Now, let's actually see what's going on here. So if we put this into a polynomial format, do a quick double check, make sure my algebra here is correct. This should be 1/2 n squared minus 1/2 n. Make sure that actually is correct there, if you will. All right, seeing nobody fussing that I messed up the algebra, what this tells us is that BubbleSort is, notice that this is a, what? It's a degree 2 polynomial. So this tells you that BubbleSort is order n squared. Okay. Now, this was actually trying to get the fewest comparisons possible. If you didn't worry about the fewest comparisons possible, so side note, what happens if you did all n passes, so you didn't stop early. What happens if you also did all n minus first comparisons each time for each pass? In other words, you didn't stop early in any way, shape, or form. Notice the total number of comparisons in that case would be n times n minus 1, which is n squared minus n. And notice that still gives you order n squared. So even if you did this algorithm in its more efficient way, which on a strictly the actual number of checks that you would do, this is, well, it is less. In terms of the actual order of the algorithm, it doesn't change the order of the algorithm. It's still, computationally speaking, order n squared, even if you were able to get it a little bit better here. Okay. So just as an aside there, even if you did this in the worst case scenario, you're still looking at this order n squared. Okay. So that's one of the ways where you can calculate the order of an algorithm. It's how many of these operations do you actually have to process? How long, roughly speaking, is this going to take? Okay. So that's BubbleSort. That's all I was planning to talk about with BubbleSort. It's considered of the what's a good way to talk about the other algorithms? There are some algorithms that are worse than this one. We are totally not doing that one. Definitely not. But the ones that are worse, most of them were developed as like an, I'm going to lie, but make it sound fun, for a giggle factor. There you go. Yeah. It's more of a, the technical term is it's for an academic exercise, because people were like, hey, let's see if we can't do this and make it work, see if we can't break it. Yeah, but in terms of things that people were actually trying to really get work done with, BubbleSort is typically one of the ones that you're considered the worst. Now, that being said, yes, there's others that are worse, as you guys have pointed out in the comments there. But that's it in terms of what I'm planning to do for BubbleSort. Next, I'm going to go over to somebody who is not this bad. Now, how do we know that this isn't the best sort of sorting algorithm there is? Let me scroll back up here. Way back before we had to write way too much. We had, in terms of the theory of the tree behind the sorting algorithm, said we should be able to, well, we're going to have to sort in at least order n log n. Well, n squared is larger than n log n. So that holds true with the theorem. But it would be nice if we could have somebody that's not as complicated as n squared. In other words, that takes less time to actually process your sorting algorithm. Okay? So what we're going to do is the next one we're going to look at is MergeSort, and MergeSort turns out to be exactly order n log n. And depending on time, we'll go over why it's order n log n, or we'll just hand wave and I may post something for you. But one of the nice things about BubbleSort is if your list is really, really close to perfect, like if it only had 2 numbers that are out of place, it's fast in that sense, but not for a random list. Because for random lists, you could actually do full computational time. All right. Oh, I wasn't too far off in thinking how much I'd have to write. All right, so we want this sorting algorithm where a number of comparisons needed in the sorting algorithm. In other words, the sorting algorithm is exactly order n log n. And so the thing that we're going to look at is MergeSort. So you start off with the exact same thing. So all of these sorting algorithms, you start off with the same thing. You have some objects. We're, in this class, going to focus in on objects that are a list of integers only because we want to, and it's easy to explain it to anybody regardless of your background. Okay, so we'll have some sequence or list of integers. You can do this with any sort of objects you want. So we'll divide this list into 2 parts. We'll roughly divide it in half, and then we're going to repeat that step each time, repeat this step 1 until we have created sublists that have exactly 1 term in each of our sublists. Okay, for this one here, we're actually going to build a tree. So what I'm going to do for this guy is very much visual in terms of the tree level that we're going to see. So much more than what you see on what we did with the BubbleSort example. Okay, the last step, and this is where MergeSort gets its name, is we're going to merge those lists back together in a specified way. Now, let us look at an example. And I, on purpose, did I? Nope, I didn't get the exact same example before. All right, so suppose we wanted to use MergeSort to order this sequence of 4, 1, 0, 3, 2, 5, 6. We want to order it numerically, in other words, ascending, so smallest to largest. Again, you can do this with alphabet letters. You can do this with other letters. You just have to have some sort of order on your objects so you know what it is, what is the desired order at the end of the day, okay, regardless of what objects you actually get thrown into the list. So here's our process. Our process was, first thing, we were going to divide our list into 2 parts. So we're going to roughly divide our list in half, and then we'll iterate. In other words, we'll keep doing that. So I'm going to write this list since they're all single-digit numbers without the parentheses, so just a string. So we have here 4, 1, 0, 3, 2, 5, 6. And the classic way, at least in math, in terms of breaking your list into 2 parts, is to partition it. And that just is done with a, what was trying to be a vertical line, but my line wiggled on me. Okay, so this is the fast way to break your set into 2 pieces, or your sequence your list into 2 sublists, 1 list of length 4, 1 list of length 3. Okay, so this is where we're building our tree. And remember, we've got a binary sorting tree behind the scenes. It's not going to be behind the scenes for this example. So you take the left half and the right half and make it the left and the right child. So we now have 4, 1, 0, 3, and on the other side we have 2, 5, 6. Don't overthink it. Now, at this point in time, we're just going to repeat the exact same thing we did on this root vertex right up here. So if we look at the list that is currently 4, 1, 0, 3, we'll divide it roughly in half. Don't overthink this. Bam. When we divide this guy in half, what happens? It'll have 2 children, and the 2 children are going to be your 2 new sublists, in this case, both of length 2. And before we get too far ahead of ourselves, let's go back to the sibling of the length 4 sublist. So we've got 2, 5, 6. You break it roughly in half, so that means 5 has to go with either the left or the right side. It doesn't matter. I'll put the breaking point here between 5 and 6. So this guy is then going to have 2 children, the left part and the right part, or the beginning or the end of the list we just cut in 2. So we'll have a sublist of length 2 and a sublist of length 1. We wanted sublist of length 1, so this guy here, he's not going to change. I guess there's no gender attached to it. It's not going to change, okay? The rest of these guys, the rest of the current children in play are dealing, or vertices in play, are currently length 2 lists. So that means we'll cut all of them in half and get a bunch of length 1 lists. So we've got one more level of this rooted tree, and we'll be done with the first 2 parts of the algorithm. So the list that was 4, 1 gets broken into 2 sublists of 4 and 1. The list that was 0, 3 gets broken into 2 sublists of 0 and 3. And the list that was 2, 5 gets broken into 2 individual lists of length 1. And just to make our life easier in the future, I'm going to bring 6 straight down. Okay. So notice here, before doing this last bit, everybody in the tree had if it had a child, it had exactly 2 children. By just bringing this 6 straight down right here, I actually created one of those guys that's almost a binary tree but slightly off, and that's why people will often say that this type of tree is still a binary tree, just because of how it got made. All right, so that takes care of steps 1 and steps 2. Okay. So remind ourselves steps 1 and step 2. We got the list into 2 parts roughly in half and created new sublists. We kept repeating this until we got sublists that only had 1 term. Done. So the next thing is we're going to merge these guys back together. Okay. Now, here's where writing it on a piece of paper, or as what I'm doing here, the electronic version of a piece of paper, is awesome, because what we're going to do is we're actually going to mirror image this tree. So I'm going to, on purpose, put a dotted line here. And I'm going to label what we just did. So this here, in terms of our algorithm, this was steps 1 and 2. And I'm going to contrast that because below this dotted line, we're going to do step 3. That's why I went ahead and titled that. Also make this a little bit smaller so we can see our tree better. We don't need the back end of the tree yet. All we need right now are the leaves right here. And honestly, the leaves are all we actually need to write the rest of the tree. So to merge these guys back together, you travel through the leaves and you just merge them. So here, we're going to take our 4 and our 1, and we'll merge them back together. And you put them back together in order. So one of the questions that I almost always get asked at this point in time is, all right, well, how do you know that you're going to get 1, 4 as opposed to 4, 1? And the thing is, technically speaking, at these merging points, you use a different sorting algorithm to go ahead and make sure that they're all in the correct order. You can, in fact, use a little baby BubbleSort right here, but notice there's only going to be essentially 1 comparison you're going to have to do, so that is totally okay. In terms of what I'm expecting from you guys in terms of this class, I'm okay with simply a visual inspection to when you merge these lists back together, you put them in the correct ascending order. Okay. Now, moving on to our next pair of leaves, and you only do pairs of leaves. We now have 0 and 3, so we merge 0 and 3 back to get to a length 2 list. Move on to the next set of leaves. So we'll merge 2 and 5 back together to get the list 2, 5. And notice right here, our 6, poor 6, it's still all by itself. Okay. Now, that's always going to happen if you have an odd number of leaves. Okay. Now, at the next level, we'll merge the vertices together. These guys are no longer leaves of the prior tree before the dotted line. So when we merge these guys together, we'll get a new leaf. Not a new leaf, don't say leaf, a new vertex. So we'll merge 1, 4, and 0, 3 together. So here we'll get 0, 1, 3, 4. Okay. And then we'll move on to the next one. And we've got the 6 and the 2, 5. This one here, you can just concatenate it together, and it actually wouldn't change. You'd actually have to do a little bit of shuffling on that last one, as I'm sure you saw. Okay. And then the last thing is we'll merge these two guys together. Notice in terms of what you're doing at each time, maybe there is actually more than one comparison. This looks like, what was that, maybe 2? Maybe 3 comparisons here if we use BubbleSort to get that back together. But you're going to have a ton fewer comparisons because you have what? You've got 2 lists that are already sorted, already ordered like you wanted to, and you are literally, put your fingers in front of your face and put your fingers so that they are interlaced, merging them together, if you will, hence the name. All right, so getting back to the final guy here, we would end up with 0, 1, 2, 3, 4, 5, 6. And in terms of dealing with the little baby sort that you'd have to do once you were merging those 2 lists, 2 would really be the only one that's out of place that would need to get moved around a little bit. Okay. Now, let me go ahead and put some space in here so that's not on top of itself. In terms of what we just did, this guy is your step 3. And that guy right there, that would be the answer, i.e. the sorted list that you care about, okay? For sure, it is. So in terms of what's going on, and that's one of the reasons why it's nice, actually let me just do this, that would be smarter. This one is significantly better in terms of actually sorting out things. This is actually, it's not exactly the same, but I've definitely, yeah, this is definitely shorter, can't speak today, shorter than the other method. But in terms of what I'm expecting from you guys with no any sort of implementation, just actually running through it on a piece of paper, this is all that you would need to show in terms of MergeSort. If you actually wanted to implement this in terms of a computer, there is a little bit more involved, and you do have to worry about what other sorting method are you going to use to merge the 2 lists together. So there's some of that implementation going into play. But in terms of what we're looking at, the overall structure of the method, this is the idea for the structure of the method. And this guy does actually turn out to be order n log n, which is also telling you that it's shorter than your BubbleSort because BubbleSort was order n squared. Okay? So that would be the idea there. Questions kind of make sense in terms of implementing these 2, at least in terms of implementing them on a piece of paper, which is all I'm going to ask of you for in this class. Please note, if you are given the original sequence right here or list, make no mistake, you can totally do it quickest in your head by just writing them yourself in order. The key thing in terms of doing these different sorting algorithms is making sure you know how to do this actual procedure. So, and key things of what I'd be looking for is all of the work to show that you're doing the right algorithm. Yeah. Yes, so the question was, is step 3 just merging and reordering? And the answer is totally yes. What you'll always get, awesome, and you can just barely see it, we'll always get below this dotted line a mirror image of the exact same tree, but all it's doing is you have split up all of the individual elements, all the individual terms of your sequence, and what you're literally doing is you're then remerging them small step by small step, and at each of these small steps, when you merge those elements back together, you do a small little reordering, as you said, or slightly sorting algorithm, if you will. And that's literally it. Don't overthink it. Now, there's tons and tons and tons of sorting algorithms, and they all have different ways of implementing them. But the goal for all of them is you start off with something out of order, you get it back into order, and then there's different ways of doing it. We did 2 of them. This one here, in terms of timing or in terms of its order, is one of the best. BubbleSort, other than some of the ones made for giggle factors, is one of the worst. But that was just a snapshot of what's going on with sorting algorithms. All right, I'm not seeing any other questions come in as I was jabbering a little bit extra there in case anybody was typing. So that's it for Chapter 3. Okay, so let us start in with Chapter 4. So Chapter 4, the first two sections of Chapter 4, I feel like they're very highly related. Both of them are dealing with behind the scenes, at least, because your author doesn't really focus you in on this for section 4.1. But both of these two sections are really dealing with finding spanning trees. Now, we've talked about spanning trees before when we were looking at depth first or breadth first spanning trees. These are going to be different algorithms. There's a grand total of 3 different algorithms here of finding a spanning tree, but specifically it's a spanning tree with minimal weight. Okay? Now, we haven't talked about weight much. We've talked about cost when we were dealing with traveling salesperson problem. So let's talk about what I mean when I say weight, and weight is actually a generic term. Okay? So first thing is section 4.1, and really pretty much all of chapter 4 has been dealing with network. We'll deal with networks. In terms of what we've done, we've actually dealt with networks a little bit in the past. A network is simply a graph where each of the edge in the graph has some function attached to it. Your author calls it K of E. It is also in other books called W of E. But even if you don't remember the name, the letter, the symbol, the K or the W, it doesn't matter. What is it? Is specifically an integer that's assigned to each one of your edges. Now, I lie a little bit depending on your situation or what the graph is modeling. You can have these numbers that are coming from this function. Your book calls it K, or other people call it W, can actually be real numbers. So that if you want to, they can be decimals, they can be negative, they can be 0, they can be all sorts of things. But standards are that it's normally positive integers. And in fact, your textbook makes a really big deal about these guys not being negative values and having to be integers. Technically, you don't need it, but you do have to adjust some of the algorithms to deal with negative numbers. So the deal here is this K of E, your book calling it K, is some function, and it represents either weight associated with the edge, weight's a generic term right here, or length connected to an edge. Technically, edges in a graph don't have a length you can measure, so the length here refers to whatever the graph is representing physically. It's also a generic term that people use. So these two guys here are typically generic terms. Your author in section 4.1 deals with length, and that's what he does for his sort of generic term. Now, this number that's attached to your edge, it can also represent cost. So that's what we did with our traveling salesperson problem. We were technically dealing with networks. Often you see with networks they have directed edges, but they don't have to. It's the fact that they have some number associated with the edge, and it's not which edge it is, it's some other thing dealing with the edge, like the cost or the weight or the length, or what we're going to see a lot towards the end of chapter 4, the capacity of the edge. And the best way to think of capacity here would be something like maybe your graph, your network, models like the classic example that everybody can picture is, think plumbing. So like the water supply lines for a city. What happens, each one of the edges in the graph could represent a length of the pipe that's carrying the water. Each one of your vertices could represent some junction in the pipe. Maybe it's where it goes into a specific business. Maybe it's where 2 pipes meet at each other. It would have to be where 2 pipes meet to each other, or it would be a graph. So it's got some of these different things going on with it. The capacity here in terms of if you're dealing with pipes, you could literally say, all right, I've got this network that's modeling the pipes in my water system on my city. Each pipe is a different size. So pipe over there can deal with, I don't know, 30 gallons per second, and the pipe over in the other part of the city can only deal with 10 gallons per second of water. What do we do? Okay. Yeah, correct. There is, in terms of what your book talks about, so the question Eamon was talking about why did it have to be non-zero. In terms of our algorithms, some of the algorithms that we're going to be looking at, the way that they're presented in your book, and I'm not going to, well, I've changed some of them, but the overall arching part of them, they often will do something dealing with you're looking for zeros, similar to what we did with lower bound with the traveling salesperson problem. But in reality, if you're modeling some situation, negative numbers come up all the time. So all you do is you take your smallest negative number and then you add that amount to everybody and pull it up to your zero or positive numbers. Okay, so that's the classic fix. And this is just to make your life easier. Instead of finding whatever the minimum value is across all your edges, look for the zero. It's a sort of standard way of doing something that makes your life easier, or the attempt is to make your life easier. Okay. All right, so what we're going to be doing in section 4.1, section 4.1 is 100% just looking over Dijkstra's algorithm. Okay, so what Dijkstra's algorithm does is you've got some sort of network, so you've got some sort of graph, it's got weights attached to each of the edges, and in this algorithm, you're typically called, those weights are typically called lengths. Okay. And we'll see an example here where I've put it totally in context. It's a big story problem and then a graph that represents what's going on in that situation. Okay? But what we're going to try to find to do is we're going to try to find a path that goes from vertex, whatever vertex you want, to whatever other vertex you want in your graph that has the shortest path, where shortest here really means minimal weight. So smallest, and the technical term is minimal weight. Okay, so notice what that means. That means you're going to have to take all of these values attached to your edges, add them up, and find the shortest one. In other words, this is very, very similar to what we were doing in our traveling salesperson problem, except there we had to go from vertex, whatever it was, back to the same vertex using a Hamilton circuit. Now, we're not going to be dealing with Hamilton circuits, and that's the big change here. It's also going to be a little bit different in terms of the algorithm. Absolutely not. So personally, I think the work is a whole lot easier, and I'm going to show you two ways to do the algorithm. Neither one of these, I don't think your book actually goes over either of these two ways. I have to admit, first time I read this algorithm in your textbook, I almost didn't even recognize it as Dijkstra's algorithm because your author talks about it in the weirdest, most convoluted, complicated way I've ever seen. So I'll show you two different ways to apply Dijkstra's algorithm. One of them is very, very careful, very precise. All of the work is shown out. I would highly recommend you doing that first way at least once. And then the second way is sort of where you can do shortcut work on the actual graph itself. So I'll show you both ways. All right. So if we look at Dijkstra's algorithm, here's what you start with. You start with some sort of connected network. So at the end of the day, Dijkstra's algorithm is going to give you a path between two vertices that has the shortest length between those two vertices. It also, just because of how it progresses, will automatically give you a minimal spanning tree. Okay? In terms of, it'll actually give you a spanning tree that has minimal weight, if you will. Okay? Now remember, what's the deal with a tree? There's only one way to get between two vertices, so that will automatically get you between the two vertices. Okay. So you have this connected network, so you need to have all of your weights. If they're not all non-negative, you adjust. What you do is you start and you're going to do a bunch of different labels, and we'll walk through each of these steps as we do it because it sometimes is a little bit, you don't always see what's happening when you first read the algorithm. So what we're going to do is we're going to have essentially a working string or a working list to deal with all of these different labels. So we're going to label our starting vertex with a 0, and that's going to be called a permanent label. We're going to be dealing with both permanent and temporary labels. Okay? We're going to label all the vertices adjacent to that starting vertex with whatever the weight, or in terms of Dijkstra's algorithm, you typically say the length it is to get to those other vertices. And then all the remaining vertices that you can't get to directly from your starting vertex, we're going to label with an infinity. Okay? Notice what these labels are. These labels are telling you how long it takes to get to blank vertex from your starting vertex. In terms of temporary, this means we couldn't get there yet. And in terms of permanent, we've already established that's the shortest way to get to whatever vertex we're talking about. Now, how do we change temporary labels to permanent labels? You pick some vertex with the smallest temporary label, and you convert that label to be a permanent vertex and call it I. So this is the step that we're going to repeat. Okay? Now, for each vertex j that's adjacent to vertex I that has a temporary label still, we're going to replace its temporary label with, and then there's a formula. So here is the formula. So j's label goes as follows. It's going to be the minimum. I don't want orange. Just a second. And this is the big formula that we're using. So it's going to be the minimum of, and there's two options. So you take the smaller of the two. The first one is the current label. Current label on j. Now note, if your current label on j is an infinity, don't pick that one as the minimum, okay? The other one should be shorter. Now, on the other side, so your other choice, and there's only going to be two choices, you're going to look at vertex I, so where you're coming from. Now, this guy is supposed to already have a permanent label. Permanent label. In other words, you've already found the shortest way to get to vertex I. So this guy should be an actual integer, some sum of the edges that you had to travel to get to I. Then plus whatever additional edge that you had to travel over to get from I to j. So this would be whatever the value is of the edge E, where E is the edge from I to j. Typically, yes. The only time that these guys are not, so the question was, step 2, are the vertices adjacent to your starting vertex, are those always going to be permanent? The only time that that's not the case is you might have something like this. Maybe 3. Maybe this is your starting vertex. Let's actually label these guys. Maybe from A to B, the weight is 1 or the length is 1. Maybe here it's 2. Maybe here it's something like 5. So if that's B, that's C, that's D. Well, the original temporary labels on B, C, and D would be the 1, the 2, and the 5. But suppose there's also an edge that connects B to C and it has length 2. Well, what we thought was going to be the permanent label on C, which would have been this initial 5, the edge that's incident to both A and C. Well, it turns out it won't be. It'll be changed up to 3 because it's actually shorter to go A to B to C instead of directly to C. So typically they are normally permanent, but they don't all have to be permanent. So you actually go and I'll show you. We're going to go through the algorithm to see how to check for all of that. Okay, but this would be the only situation really where those vertices adjacent to your starting vertex would not be permanent. Notice, though, at least one of them has to be permanent, whichever one's the shortest length right there. All right, so that's the basics of Dijkstra's algorithm. What do? You then iterate this step 5. So let me actually put that down here. So 6, repeat. Wow, that's not how you spell repeat. Let me fix. Repeat steps 4 and 5 until all labels are permanent. And that's how you would close it off. It depends, and it could be none of those two. So the question is, in steps 4 and 5, are temporary labels equal to either infinity or the weight on the individual edge? And the answer is, if this vertex I was one of your original vertices adjacent to the starting vertex, it would start off with being whatever that edge value was. However, that's only true the first sweep in. Once you get in the middle of your graph, It actually turns out that these temporary labels that you're dealing with on I are typically some sum of the KEs that you had to use previously, as you keep adding KEs. Now on your J could totally be an infinity, or it could be some other number. So yes, it could be one of those two options or a third option as well. So let's actually jump into an example, okay? So this is the algorithm. The only other thing left that I wanted to talk about is the length. So remember what our goal is. Our goal was to find some path between two different vertices that you'll be told who the vertices are, and you wanted to find a path with shortest length, where shortest length, the length here refers to your KE function, those numbers on the edges. So it turns out your shortest path from vertices, and I just went ahead and picked vertices here of A and Z. It's standard for future networks to deal with A and Z to be your start and your end. But what it is it's simply going to be this length given by a lowercase delta is the sum. Well, I shouldn't say the sum. It is actually the permanent label on Z. So that's one of the reasons why we care about these permanent labels. As soon as you get a permanent label on the vertex you were trying to get to, the ending point on your path, that permanent label will actually tell you the shortest path to Z is. Why? Because each of these permanent labels, once it converts to permanent, is actually telling you the shortest way to get from your starting vertex to whatever vertex you're on. Okay? So let us see how all that works in an example. So the example that I've got prepped up for us is this guy. Okay, so I did two things for us. One, I prepped the graph like I normally do, but two, I actually put some context with this so you can see some of the reasons why people talk about length for this algorithm. So this is in reference to some power plant. I'm totally picturing like electrical lines being strung along a road. Okay? So suppose you have some power plant, and when power is sent from plant 1, which is represented by vertex 1, to city 1, which is represented here by vertex 6, it's going to have to pass through a couple of relay stations, and these are represented by the 4 vertices, vertices 2, 3, 4, and 5. Okay? So this network gives the how the different things are oriented, the power plant, the city, and the relays. It also gives the distances in terms of miles between the different items. So between power plant 1 and relay 2 and 3, you've got 4 miles and 3 miles respectively. Between relay 2 and 3, you've got 2 miles respectively. Okay? And in terms of the arrows here, this is indicating that the power is, or whatever, is going roughly in that direction. Dijkstra's algorithm does not require you to have directed edges, but it's definitely in the first example that you have easier to see it with directed edges. Okay? So this would be the graph that we're looking at. Now, what we would like to do, or I shouldn't say that, the power company wants the power to travel the minimum distance from the power plant to the city. Since their cost is to some extent dependent on those distances, I'm assuming where I pulled this from that was because of things like running wires, et cetera, okay? So that's one way to put distance or length attached to your edges. Now, in terms of actually implementing Dijkstra's algorithm, do we actually need to know any of that context? Nope. All we're going to need is that particular graph, okay? So what we're going to try to do is we are going to try to find the length of the shortest path from vertex 1, which it looks like I missed it in typing, to vertex 6. Okay? So let me put in, this is where we want to start, and that is where we want to end. It is extraordinarily important to know where you're going to start and where you're going to end. In a directed graph like this, hopefully it's obvious because of the direction of the arrows, but in an undirected graph where you can also do this algorithm, it's important to know where to start and stop because, well, you can't do the algorithm if you don't know where you start. All right, so if we go ahead and apply this algorithm, here's what you do. So I'm going to first show you the full-on version of the algorithm that shows all the steps. I'm going to write out all of the steps, and then we'll show the shortcut version of the algorithm. Okay? So each of these vertices I'm going to label 1, 2, 3, 4, 5, and 6 for our 6 vertices. And this little sequence right here, this list, is going to be the labels, both temporary and permanent, for each one of our vertices. So according to our algorithm, what do we do? First thing is you took the starting vertex, which is vertex 1, and put a permanent label of 0 on it. So that's the first thing. Now, second thing that you did is you found all of the vertices adjacent to your starting vertex, so that in our case, the 2 and the 3, and the labels that we put on vertex 2 and vertex 3 corresponded to the function, the weight function, or in this case, the length function on the edges that got you from vertex 1 to vertex 2 and 3, respectively. So the label that we'll put on vertex 2 is going to be 4. The label that we put on vertex 3 is going to be 3. Notice I just pulled the numbers from the edges. Don't overthink it. Now, those 2 and 3 are the only 2 vertices that vertex 1 is adjacent to, so everybody else gets a temporary label of infinity, and this is how you initialize it. Initialize. At this point in time, only the 0, and I put a little asterisk on the 0 to indicate that it's a permanent label. Only the vertex 1 here has the permanent label of 0. Everybody else at this point in time, you can assume, has a temporary label until we have confirmed otherwise. Okay? Now, next thing that you do is you look through all of your temporary labels and you find the smallest ones. You look through all of these numbers that don't have an asterisk next to it. You guys tell me, which is the smallest number? Don't overthink it. Yep, definitely the 3. So once you've established that 3 is that smallest number, and if there's a tie, you get to pick whichever one you want. It doesn't matter. You're going to convert this guy to a permanent label. Okay? So what did we do? We picked on 3. 3 got converted to a permanent label. Okay. Now, once we went ahead and were at 3, what happens? Well, you look at 3 right here. And I'm going to go ahead and highlight this, but I'm going to highlight it in a slightly different color. Not really a highlighter, which is why I was trying to be careful with that line. Okay, so we're currently looking at 3. You look at all of the vertices that are adjacent to 3. Now, this is a directed graph. Any guesses who I mean when I say vertices adjacent to 3? What do you think those vertices are going to be? Correct. It's only going to be the vertices that you can go to from 3. So we're going to look at vertices 4 and 5, those guys being the only vertices that you can travel to from 3. Now, this is where you grab their new label. Okay? So right now we are dealing with steps 4 and 5, and we're repeating steps 4 and 5 until we get done. So to indicate this, these first 3, this just initializes that sequence of labels. Those 2, you keep on repeating until you're done. Okay? So the next thing we're going to do is we're going to calculate the new label on vertices 4 and 5. So we're going to do this whole formula right here, which I'm sure there is a better way of writing it out, but I did it in words just to make it easier for you guys. All right. So if we look at vertices 4 and 5, you take their current label. So we're taking the minimum of their current label. Oh, I did not mean to have that be yellow. I guess technically it's not yellow, it's orange. All right, so new label on vertex 4 is going to be the minimum of its current label, which is infinity. And then what do? You take how long it took to travel to vertex 3 right now. In other words, the permanent label on vertex 3, which is 3, and then plus the additional amount it takes to get to vertex 4. So as of the work right now, this is the shortest distance to get to vertex 4 by going through vertex 3. Okay, so you add the 3 we already have to the 2. Now, don't overthink this. What's the answer to this expression? Yep. don't pick infinity. The other answer will always be a number. Okay? We're going to do the same exact thing on vertex 5. Here, you'll take the current label on vertex 5, which is infinity, because we hadn't gotten there yet. You'll take the 3, because that's the permanent label on vertex 3, or how long it took you to get to vertex 3, or what the weight is to get to vertex 3, or the length to get to the vertex 3. You'll then add the weight or the length of the edge, 3 to 5. In our case, that is 4. So what should this answer actually be? Yep, so that should actually be 7. Now, these are new values on the labels of vertices 4 and 5, so we're going to replace the infinities with those 2 new values. So we have 0, which is permanent, 4, 3, which is permanent, and then 5, 7, and we still have an infinity at the end. And let me go ahead and label these with which vertices they're corresponding to. Okay. And then you repeat the process. Notice the only 2 permanent labels right now are the ones with asterisks. So if you scan through this list of labels, which vertex should we focus on next? I think you're thinking the right thing, but I worded it different. Right, it's vertex 2, and the label on vertex 2 is 4. So next, we'll go and we'll look at vertex 2, or label 4. So if we take vertex 2, we're going to change that 4 to a permanent label. Notice because vertex 2 was not adjacent to vertex 3, we didn't have one of those situations where we're going to come back around and get to vertex 2 by way of a different way that's shorter than 4. So in this case, this guy gets to be a permanent label. But we waited to make that call until we actually got to this stage. Now, at this point, we're going to look at the vertices that are adjacent to 4. So you have to go back to the graph at this point. So if we go back to this graph, and currently we are looking at vertex 2, and we just came up here on 4. So who is adjacent to vertex 2 in the graph, or technically network? Both 3 and 4. Now 3 already has a permanent label, and this happens every so often. So you check. And this permanent label said you have a length of 3 to get from vertex 1 to 3. But if you had to go through vertex 2, you have a length of 4 plus 2, which is 6. Do we need to change our permanent label? Remember, it was permanent. We're not supposed to be able to change it. So do we need to change our permanent label on vertex 3? What do you guys think? Nope, we've already established that this guy right here is the shortest way. We could get from 1 to 3 by way of 2, but it would take a length of 6 versus 3, so no, we're just going to leave it alone. Now, you can totally, if you want to, and this is one thing that I have to admit when I first did this algorithm, if I had 3 was adjacent to 2, I was like, I'm checking it again. And I would throw it through this same algorithm and find the minimum of what its current label is and what the new label is, and it never changes. So it's personal preference. You can always just look at your temporary labels, your non-permanent labeled vertices that are adjacent to 2. You would not. So if you did end up changing 3 right here, that goes here, 4 and 5 would, I was about to say something that wouldn't, in a directed graph, yes, they would actually change. So they're never going to actually, in reality, change. Here's why. Notice we picked 3 to visit first because the weight along this edge was 3, which is smaller than the weight along this edge 4. So there's no possible way that this permanent label right here is going to change. However, if you made a mathematical error and this changed, yes, you'd need to go back and check your labels on 4 and 5. If you're dealing with an undirected graph, it should actually all even out in the future just because you have more options of what you're doing, but you'd want to go back and check those labels as well. So knowing logical if-then statements, if the if part was actually true, the answer is yes, but in reality, you're never going to get to that if part of that statement. You should never actually change a permanent label. Where were we? Right. So we were looking at the guys adjacent to 4. So we said they were vertices 3 and 4. 3 is permanent, so we don't have to deal with it. So 3 and 4. 3 is already permanent. But let me go ahead and show you what would happen if you just went for it. So this one here is current label on 3 is 3. And then the current label on vertex 2, which is 4. Plus then how much it costs, or the length from 2 to 3, which is an extra 2. And this is exactly what several of you already said, no change to the label. Okay. Now, if we look at vertex 4, the new label on vertex 4 is current label on vertex 4, which is 5, pulling it right here from our list. And we're going to compare that to the current weight or current length to get to vertex 2, right here. And then we're going to check to see how much further it takes to get from vertex 2 over to vertex 4. So we'll add in that 3, so plus 3. Now notice this is the first time, well, it's not really because we did a permanent label on vertex 3 as well. But if we had ignored our permanent label on vertex 3, notice this is one of the times where we have a true comparison of two numbers. We're not actually putting a new label on a vertex we couldn't reach before. We've actually reached this vertex 4 previously a different way, and now we need to compare those two different ways of getting to vertex 4. So which do you think? Which of these two labels should we keep? In other words, what should I write after the equals sign? Yep. So if we use vertex 2, I think I'm going to need to just copy that graph down here so we can see it. If we actually use vertex 2, it takes longer. It takes a length of 7 as opposed to 5. So we're going to keep that length of 5 right there. At this point, we put in our new labels. So we still have 0 that's permanent, 4 that's permanent, 3 that's permanent. The label on 4 stays 5. The label on 5 we didn't touch. And the label on 6 is still infinity. So really that last step, all we verified was we did good at the previous step and we got the permanent label on vertex 2. All right, so let me go ahead and actually copy this graph so we can see it as we're working a little bit further down there. Just because I don't want to zoom in or out too far so you can actually read the letters and the writing. I think we can probably put it, what, maybe there? And we'll zoom this one, of course. All right, and we'll make that a little bit smaller. We'll just move it right there. That'll be better. All right, so this is where we're currently at. So we've got permanent labels only on the circle guys. Now, at the next step, you again look through all of your labels. You find your smallest label. Roughly speaking, yes. So there's a question that I didn't see as I was attempting to move that graph. So let me pick that question up. And the question is about vertex 4 becoming permanent. So the actual algorithm tells you that every label that is not permanent, you're going to go and focus on the smallest one next. So vertex 4 next will become our next smallest weight because it has a current weight or length of 5. So that'll be the one we target next. It'll automatically become permanent. But you're right, in terms of why the algorithm is doing what it's doing at this stage in the game, by having 5, the smallest label that isn't permanent yet, it means that we've already dealt with all the different ways of getting to this vertex 4 at this current moment in time. So yes, good call there. That is exactly why the algorithm is doing what it's doing. Okay. And you totally answered the question of what I was about to ask us as well, which is, who is our next vertex that we're going to make a permanent label? It's going to be vertex 4. So here, vertex 4 will turn into a permanent label. We'll go ahead and start right there. Now, once you've turned vertex 4 into a permanent label, who's adjacent to vertex 4? Only vertex 6 in terms of leaving vertex 4. So we are, yay, getting to that vertex we wanted to get to because we wanted to get to vertex 6 there. And let me go ahead and tag this guy as a permanent vertex. Now the label on vertex 4 was 5, and that came by way of vertex 3 is how we got that label 5. Now, when we look at vertex 6, what happens? We're totally looking at changing its label. It's currently infinity, so we're definitely going to change its label. And we're going to look at the current label on vertex 4 that is now permanent. That label is 5. And we're going to add something to it. What should I add to it? What should be after that plus? Three. Yep. So 3 would be how long it takes to get travel from vertex 4 to vertex 6. So we'll totally add the 3. Notice it's 8. It doesn't matter what it is. As long as it's an integer, it's better than infinity. So we've got an 8 right there. And that will be your new label for vertex 6. And while we were doing that, I went ahead and recopied our string of labels, both temporary and permanent, although we have mostly permanent labels right now. Now, who would be the next vertex that we're going to pick on? Should we look at vertex 5 or vertex 6 next? Yep, vertex 5, because that's the smallest label of a non-permanent vertex. So we'll convert our vertex 5 into a permanent label. In the graph, let me go ahead and draw a yellow circle around the vertex to indicate it's now a permanent label. And this label was 7. And to get to 7, remember, we got to 7 by way of vertex 3. So I'll go ahead and highlight how we actually got to vertex 5 along the way. Okay. Now, once we're looking at vertex 5, who's adjacent to vertex 5? Don't overthink it. Who's adjacent to vertex 5? Yep, vertex 6. And in fact, when we're down at this level, notice there's only one vertex without a permanent label. Since you don't have to worry about checking vertices with permanent labels, you say, hey, well, it's obviously just the last guy as long as there's an edge connecting you to that last vertex. So we'll go ahead and we'll see about adjusting the label on vertex 6. So just as a heads up, we didn't see it much in this graph just because it's a relatively simple network and because of directed edges. If you have an undirected graph, so a simple graph that's also a network, one of the ways to actually progress through the graph so you don't just keep going around and around in circles is once you have a label that's permanent, you move on. Don't ever go back to it. Here with the direction on the arrows, you're doing good in terms of those arrows are the direction is naturally pushing you through the graph. But that's one of the reasons that you don't, it's not the only reason you don't have to go check permanent labels, but that's one use of permanent labels. Where were we? 6. So current label is 8. So what should I put after the comma there? And I'll go ahead and actually put it in terms of plus just so that everybody is comfortable with what we actually did. But what should I write after that comma inside the curly braces? In other words, the second position. It's going to be 7 plus something. 7 comes from your label on 5. What would be, Ooh, almost. You're reading off the wrong vertex. Yeah, there you go. So we're currently on vertex 5. So at vertex 5, we're currently, the label on 5 is a permanent label of 7, so it's 7 plus the additional edge right here. So 7 plus 7, or 14. So what should be our actual label on 6? Does it need to be adjusted? Or should we keep the label on vertex 6 as 8? So what do you guys think? Keep the 8 or change it? There you go. We'll keep the 8. So in terms of this guy, we'll get 0, 4, 3, 5, 7, and 8. Now put the labels up here at the top. Now, any guesses why I went ahead and put a star on that last location, on that last 8, the label on vertex 6? Probably should have made it in orange, but it didn't happen. Ooh, so both the answers all the answers so far that have come in are correct, just different ways of saying the same sort of idea. So yeah, our next step would have been, find my cursor so I can show you guys. Our next step would have had all of this same work that we had previously, except no marking to show that vertex 6 is permanent. Well, then you'd look at your temporary vertices, pick the smallest one, which is there's only one left. You have to pick the 8 and make it permanent. You can also think of one of the ways that you're doing this is because this is the very last label that wasn't permanent, you don't have any other choices. You have to make that last label the permanent label. Or the last vertex that didn't have a permanent label, it has to turn into be the permanent label. So when you get to this stage, once you finish off dealing this guy, that is automatically going to be your final answer in terms of labels. So I'm going to throw, oh, go ahead. Yes, if there was a 6 to 7. Oh, do you mean an additional vertex after the end over here? Ah, okay. So if you remember in terms of how we got our labels, this one we did do it relatively in order, but in terms of how you actually get your labels to turn into permanent, it can be in all different orders. It doesn't have to be sequentially. If your two vertices that you're looking at are relatively close to each other in the graph and you have a much larger graph later on out, yeah, you could probably terminate your algorithm a whole lot earlier. There would have to be some sort of judgment call. So if it was if you had automated this algorithm, you'd have to have some sort of stopping point. And this, by getting all permanent labels, would be that automatic stopping point. However, if you're doing it totally by hand, if you can visually see that, yeah, you don't need to go any further for these guys over on the edge here, much further out, you could stop prematurely, if you will. So yes, that is something you could do. In terms of often what happens, though, it's pretty common when you use Dijkstra's algorithm or doing these sort of things, it's pretty common that you're not looking at two paths that are close to two vertices that are close to each other in the original graph. It's pretty common that they're on opposite ends or close to opposite ends in the graph. So it is, you often see that you go all the way out in the algorithm, but no, if it's in a smaller initial part, you would not need to see the ending part. But again, if you were automating this, you'd have to figure out some way to have that termination. All right, so what I did while we were talking was I went ahead and initialized a poll everywhere question that is totally on this exact question, and it actually gets us to the conclusion or half of the conclusion of this particular question. So see if you guys can answer this question. And the question is, what is the length of the shortest path from vertex 1 to vertex 6? So while you guys are thinking of that answer, I'm going to go ahead and just copy down what it says up on the poll everywhere question over here. So answer, or really conclusion. Don't overthink it. You guys have all the information you need. And I'll go ahead and share this with you guys as well. That way you've got the URL. Make it a little bit bigger. I'm not sure if that size actually changes on your guys' screen or not. Something I need to demo at some point. So the question that I had is, if I resize my screen, does it resize on your guys' end? Or does the size not matter if I resize my screen? Okay. So then I don't need to worry about that as much, because I try to resize them sometimes so you can see them bigger, and if it doesn't change it on your end, then there's no sense for me doing that. Thank you for the info. All right, so I'm going to get rid of the poll everywhere side. That way you can see the question that we were working on much bigger. I know everything shrinks for you. All right, so let us see. Overwhelmingly, you guys have guessed that the length of the shortest path here is 8, and that is the correct answer. So the question is, where did you get it from? Don't overthink it. You totally, theoretically, hopefully, got it from the label right there on your algorithm we just did, okay? Now, in terms of if you want to actually find that path, you had to keep track of how we got this length of 8. Notice what I was doing while we were doing our algorithm. Except for the last step, I was actually building ourselves a spanning tree. And specifically, what did I do? Every time we had a permanent label, I put in the edges of how we got to that particular label. Yes, so it's not just any old path, it's a directed path, if you will, because you have to follow the directed edges. So here, notice, if we had actually wanted to find the shortest path from 1 to 4, this spanning tree actually tells you how to do it. It go 1, 3, then 4. If you want to get all the way from 1 to 6, we're going to follow the only way to get there, which in our case, please don't make that black. I did not. It'll be 1 to 3 to 4 to 6. And notice that's relatively straightforward to follow in that spanning tree. So this guy is a spanning tree where at each one of the leaves, I shouldn't say leaves, at each one of the internal vertices or leaves, it's the shortest distance from this starting vertex from the root out. Okay. Now, we're currently at 1, which is our official end time. I can probably, in about 3 minutes or so, show you the shortcut way. Do you guys want me to show you the shortcut way for this algorithm right here without doing all of the work we just did? Or do you want to do that at the beginning of next time? Okay, I see lots of yeses. So first thing is, let me go ahead and recopy this graph. Did I put too much work on this graph? I put too much work on this graph. So way 2. Now this way 2 is totally mimicking something we're going to do in the future, but it's also just straight up a shortcut. So we had our vertex 1, we went to 2, we went to 3, we went to 4, we went to 6, 5, 3 to 5, there's another edge, it went down. You need the weights, you can't do this without the weights. 4, 3, 3, 2, oh, I missed 1, 2, 4, 3, and 7, and that should be the whole thing. So in this case, what we're going to do is we're going to do the exact same labels. I shouldn't say that. We're going to do labels like before, but we're actually going to have 2 things. So in terms of our label, it's going to look like this, here, and here, So the actual label like before, in other words, the length of the path will be the second position. The first position is the last vertex we visited, okay? And what we're going to do is we're just going to put these labels on the individual vertices in the graph. We're not going to do any of the other scratch work. Now, if you want to use a shortcut way in the future, I'm totally fine with that. Please note, though, there's almost no way to show your work with a shortcut way. So if you're wrong, I can't give you partial credit easily, okay? So I would definitely recommend, if you're going to use this shortcut way, do it the long way at least once. Okay? So what you do for the first vertex, notice you can't come from anywhere because you are starting at that vertex 1. Okay. So here, in terms of the weight, it is 0, and that is the permanent label. Okay. Next, what do? I'm going to underline it when it gets permanent. We then, over on 3, so you take your shortest one over. This one here, we came from 1, vertex 1, and it currently has a weight of 3. Bam, done. Now, when we go out from here, what happens? We can say, hey, you know what? We want to label everybody that was adjacent to 1. So we have here, go from 1 to 2. I'm not going to underline it yet. We came from vertex 1. We have a weight of 4. We'll come back and adjust as needed. We know we're not going to because we've done this problem already. At 3, you're looking for the smallest weight, the smallest length right here. So we go out. At 5, it came from vertex 3. We add 3 plus 4. So that gives you 7. Okay. We haven't yet established that this is the smallest one, so we'll come back to it and underline it when we're done. Over here at 4, we came from vertex 3. We add 2 plus that current weight of 3 to give ourselves 5. Okay. At this point, we look for the smallest weight, or the smallest length. That's the second position. So we go over here at 4. We say, hey, nobody's smaller than 4, so that has to be the permanent label. We go out. Oh, this guy here is a weight of 3. It's smaller than 4. It's already permanent. We're not going to change it. And when we go over here, we say, hey, this weight or length is 5. If we add 3 to 4, that's 7. 7's bigger than 5, so don't change this guy either. At this point, we didn't change anybody going out from vertex 2, so we look at these two. We see the smaller one's 5. We only go out in this direction. So at vertex 6, we came from vertex 4, and we have 5 plus 3, the weight we traveled, so that is 8. Then we say, hey, of the remaining 2, this one we isn't permanent yet, so now we're going to make it permanent. We'll then look from traveling from vertex 5 to vertex 6. We say, hey, 7 plus 7 is 14. That's not smaller than 8, so no changes. And since this is the last one that we haven't dealt with, it is now permanent. And what does this tell you? This gives you the exact same information. Notice the 8 right there tells you the length of the path is 8. And here you can actually backtrack. Notice this first position tells you where to go. So this says go back to 4. This one says go back to 3. This one says go back to 1. And you can actually put in the other parts of the spanning tree as well. For these guys not on the path you cared about, notice vertex 5 connects back to 3 from that first position. And vertex 2, I did not mean to do a circle there. I was using circles to represent other things. Vertex 2 connects back to 1, and notice with the 2 highlighted colors, you get that full spanning tree. And I did it in 5 minutes instead of 3, but we gave you some extra information because of the spanning tree. So notice, same thing, definitely tons faster here, but you are not showing any of your work because you're doing it all in your head. So I would definitely recommend doing that other way one first, at least one time before you do this second way here. Okay? But yeah. If you want to use a shortcut method, you totally can. Questions? Make sense? Down. Yes. Sorry. Let me actually get rid of this part right here. That is the entirety of way 2. And the yellow part is that same shortest path. That is a good question. So what I typically do in terms of credit, if you're asked to do a specific algorithm, I have to see enough work to show that you actually did the algorithm, okay? So as long as you show enough work that you actually did the algorithm, that's fine. If you got everything right, you'll get full credit. But if you got something wrong If you don't show all of the intermediate steps, especially where you went wrong, I can't always show you extra credit in that. Not extra credit. I can't always give you partial credit in that sense. So it's always a hit or miss, especially on some of these guys that you can totally just read off the graph. If you don't want to show all the work, I'm not going to fuss at you as long as you show enough of the work to show you did the algorithm you were asked to do. Okay? But if you're concerned that you didn't get the answer correct, I would recommend showing more work. That way, because in that sense, if you didn't get it right, I can show you, I can give you partial credit or show you where you went wrong, et cetera, et cetera. Okay. So I'm going to go ahead and close down the recording here. I'll stick around for questions. I see I've got a couple extra questions coming in right now. I'm going to go ahead and shut down in terms of the recording. But that's it for today.